Today I'm going to talk about our work at SAS about transfer learning for education data. This is joint work with my group, Elknar and George. So basically, the first thing I want to talk about is small data in the age of big data. So we've heard everything about big data these days, and every data set seems people are talking about huge, like terabytes of data. But in my research, in my PhD, and my work, what I've seen is, although there are many questions, many problems associated with these extremely large data sets, also a lot of researchers are struggling with not big data, but small data. They can't find really good, high-quality data set that suits their needs. That's a lot of reasons behind these. First thing is, obviously, there could be difficulty in data collection and regulations about what data you can share with researchers, what you cannot, who can work on it. And also, in the changing environment, changing population, the data you collected like 10 years ago may not apply to today's situation. And also, the need for separate models of subpopulation groups. What I mean by that is we want personalized models and models for specific, like minority groups for each different regions, and that all together restrict the size of the data set a lot of the people have. So I take an example of NC State University student data set. So that's a data set we got from the school, which is actually a pretty good typical data set you would get. It has its data collected over 2 semesters, so over a year, from over 7,000 students in a total of 9 different colleges, over 100 departments. So on the surface, it looks like a very good data set with plenty of data, and they actually collected quite some detailed information. There are over 200 variables, including different kinds of demographic information, academic information like what schools they were in, what rankings there were, what are their SAT scores, and what classes it took in these 2 semesters. So those are very good information, but when you break it down, we all know that students from different schools, from different departments tend to take different classes, and their features don't always align. Like students in engineering school won't take the same classes as students in humanities and social science. So many times we want to build separate models for them. But if you look at, of the over 7,000 students, if you break it down by just colleges, you end up with students, the largest school is engineering. You have barely over 1,000 students there. And remember, we have over 200 variables. And that no longer looks like that big a data set. If you further break down that engineering college, we have 28 different departments, and even the largest departments. This 300 is undesignated, so this is undergrad students. They haven't decided which department they're going to be, really. So the largest department really you have is mechanical engineering, which only has data from 158 students. And the smallest, over here, we probably only have 3 students or 2. So that's really a problem, and when you want to build a specific model for your specific problem, like say I want a good model for my electrical engineering department, I only have data from 56 students. How do I do that? So we have to use some help from outside data. And how do we do it? If we just blindly borrow data from outside, then we're no longer focused on our own department, so there is a balance to strike. So what we attempted to do is to borrow some techniques from the transfer learning. This is a new field, very hot these days in machine learning. For people who are not really familiar with it, the basic idea is you borrow either the model or the data from some other task that's not the problem you're directly working on, but is related to your task, and try to make use of their data or their model. So naturally, people do this. For example, when we learn a new computer language, if you have learned C++ before, learning Java would be much easier than you starting from scratch. So we naturally apply the concepts, the basic ideas to a different field of study. Transfer learning is the same thing. So instead of traditionally you have 2 separate pipelines for each different task, Now you assume the tasks are actually related, and you build a learning system to borrow some knowledge from a different task and use it on your specific model. There are two basic classes of transfer learning. People classify it slightly in different ways, but I see it as the biggest departments are, first you transfer data. So you either filter or weight related source data sources, the related data that's not your specific task. Or you align the source data with your specific target. And the second class is you transfer model, where you could either start from a previously trained model, or you borrow some part of that model's parameters and start from there. So the one we're talking today is the filter and reweight data, because the problem we're having really is we have a small data set, really small for our own department. The technique we're using is called Trade Boost. It's boosting for transfer learning. It's built upon a very popular boosting algorithm called AdaBoost. So we use this. There are many good things about this. First of all, it's it can use so it's a classic algorithm. So it's easy to implement and it's easy to interpret. So that's important for a lot of like the applications where you have government regularization or things people care about. They want to understand why they're making such predictions. So the idea of this algorithm is transfer weakly related or outdated source training samples to a new task to improve performance. So the data set will look like this. So here is the validation samples, the real data you want to build a good model for and test on it. But then you only have a small data set to train on, which is directly related to your task. Then there is a large data source that's not directly related to your task, but you know there's some relationship between them, and you want to somehow borrow some samples from there to help you train a good model. So to do this reweighting, what the algorithm does is it's an ensemble algorithm. So at each time, it trains a weak learner on all the data you provided, and then it knows which is your target data, which is your source data. And for the target data, if you make a wrong prediction using this model, then I try to focus more to make it right. But for the source data, which you know some data are related, some are not, then basically it does is apply this model, and if it does the correct prediction, I say, okay, this data is probably related to my task. So I increase the weight for that data and downweight the other data. So in this process, iteratively, you select some data, give them different weights, and filter out what data is more related to your target. So here we use these algorithm on the data set we were talking about. So in the end, we actually only used 125 variables because some of the variables actually have a lot of missing data. So after data cleaning, there's 125 variables. And the target source, the task we're focusing on, are students from 3 departments: electrical engineering, bioengineering, and computer science departments. Basically, we combine those 3 because the students there tend to take very similar classes and they have similar features. And the source, so the big data set that we are borrowing from, is all other students, regardless of their departments. And here, the 2 training sets for our target, we have 140 target training samples. That's barely more than the number of variables we're using. And in the source set, we have over 6,000 students, and we validate the result over 325 students from the 3 departments we're interested in. So we compare the Trade Boost, which is the transfer learning boosting algorithm, with the AdaBoost, which is the classic boosting algorithm. So the 3 lines, this is the transfer learning, the green line, transfer learning algorithm. The red line is AdaBoost, the traditional classic boosting algorithm on the entire school data set. So we don't distinguish between the engineering departments and other departments. We just say, okay, give me a general model that I'll see if it works for my department. And the blue line is the traditional boosting algorithm on only the 3 department students. So let's say, okay, maybe the other students don't work for, their data doesn't work for me, so let's just train our small data set and see how that works. So in the end, you see the training on only the 3 departments has the worst performance. It's actually worse than the general model on all the students. This is a direct result of overfitting because you have so few students. But when you use the data you have on hand to guide the selection of borrowing from the source data, you actually improve the performance and get the best result using that. So quick summary. This is a method of transfer learning. And again, there are many different transfer learning algorithms available. And I do think this is one that's easy to interpret, and you can use it because it's an ensemble algorithm. You can use it with different weak learners. So it's very good algorithm for this specific task. But again, there are many transfer learning algorithms for different tasks and different things. And we plan to work on that in the future as well. The question we had after seeing this result is actually, so this works for these 3 departments. Are there situations that transfer learning, especially Trader Boost, doesn't work? So we also found those. The first situation is there's no need for transfers. So what if the students, so your task and the general population are the same? Then there's no real reason to try to reweight the data. It's best to just build an overall model using all the data you have. The second situation is really you're facing with too small a data set. Let's say you have over 100 variables, but you only have 10 students. So the student population is no longer is representing your model. You cannot possibly guide the selection of data using only 10 students. So in the end, that costs, the better thing to do is still build an overall general model. And we have experiments showing this. So here, the first one is the target and the source are both just randomly sampled from the whole student population. So there's no difference between the 2 data sources. And you see Trader Boost actually does the worst because in the process of reweighting, you bring in some bias by selecting using the guided part of the data. So you're biasing towards that part, and it brings more error. So training on all the data is actually the best. Here, the other example is paper science students, where we only have 17 students. And this is also the same, so if you only train on the 17 students, you're going to get big errors. And it's the same for Trader Boost because the 17 students, you're overfitting it too much, and you're ending with bigger error. And still, when you really don't have a good data set, it's too small to train a reliable model. It's better to use a bigger data set that could be a little bit more general, but still usable. All right, I think we have a few minutes. Thank you for your attention, and any questions?